All right, so talking about probabilities, oftentimes we have multiple things that we're trying to find the probability of an outcome for. So that would be something like pulling a ace from a deck and then pulling a 10 from the deck, okay? Two different actions. Or looking at things that have different parts. So a dresser has a green, blue, and purple shirt, and a red, orange, and yellow pair of pants. What are all the possible outfit combinations? So I'd like you to pause and take a minute and write out all those different combinations. So hopefully you've written out those combinations. And so there are 9 total combinations. Often it can be hard to make sure that you have all the possible outcomes written, especially if there are like 3 different steps, right? If we added in socks and a hat and things like that. Or if we have lots and lots of options. So we have a method to help us to write these out. Now the first thing that I want to highlight is what you just created. You just made a list of the total possible outcomes of a situation with more than one part, and that is called a sample space. Sample meaning like all the possible things it could be, right? It's a little bit of each. It's the sample space, all the total possible outcomes of the situation that has more than one part. Now the tool that we are going to use is called a tree. And if you think about a tree starts with a branch or a trunk, and then it branches off, and off of those branches it branches, and off of those branches it branches off, and it makes kind of like a web or a tree. And so this is the idea that we're going for. We're writing out our possible options as things that are branching off of the thing from before. So we're going to take our same situation, and we're going to represent it in a tree. Now I'm going to say green is G, blue is B, P is purple. Okay, I'm going to do some abbreviating. It is super common to see abbreviations in trees. Okay, my first step in my tree is looking at the dresser has a green, blue, and purple shirt. So my first step is going to be to include the shirts. And there were 3 possible outcomes. So I'm going to write 3 branches on my tree for the shirts. I could have green, I could have blue, or I could have purple. Okay, that takes care of my options. There are no other options. Now, no matter what my first choice is, if I had green, blue, or purple, I have 3 choices for the pairs of pants. So if I have a green shirt, my pants could be red, orange, or yellow. If I have a blue shirt, my pants could be red, orange, or yellow. And same thing goes if I have a purple shirt. I have 3 options for what my pants could be: red, orange, or yellow. These might make some interesting looking outfits. But this shows me all of my possible outcomes. Now, the way that I make use of this is I look across my tree. So I always start here, the furthest to the left, and I carry myself down the highest up branch until I hit the first thing. Okay, well that is green. And the next thing that comes after it is red. Okay, so green and red. Now, one thing we did not include that most trees include is a probability. So we're going to take a minute and write in the probabilities of each thing happening. Well, the probability of pulling a green shirt out of a green, blue, or a purple shirt is 1 out of 3. It's the same probability for the blue and the same probability for the purple. So on the branch, we write what the probability is of that thing happening. Now, if I focus in just on the shirts, the probability of pulling a the probability of pulling a red shirt or pants is 1/3, 1/3 for orange, and 1/3 for yellow. And it doesn't matter whether or not I have a green shirt or a blue shirt, the probability for the pants stays the same. So now that I have my probabilities on there, I can include them in my sample space, in my outcomes. I take the probability on the first branch, and I multiply it by the probability on the second branch. Okay. When I multiply fractions, I multiply the top numbers, so 1 times 1 is 1, and the denominators, 3 times 3 is 9. Okay. That gives me my first item in my sample space. Green and red is a 1/9 chance. And if I was being really good about my notation, I would have my P parentheses to say the probability of green and red. Now I'm going to take the probability, I'm going to follow that same branch, green, but this time I'm going to follow the next branch, orange. Well, I have a 1/3 and a 1/3 chance because those are the probabilities written, so it's 1/9. Lastly, I'm going to follow the last branch within the green branch. So I have probability of green and yellow, which is also going to be equal to 1/9. You'll notice that they all have the same probabilities, so they're all going to equal 1/9. Once I've exhausted all my options, then I go down to my next branch. So now I have the probability of blue, start at the top of the next branch, and red. Then the probability of blue and orange, then the probability of blue and yellow, okay? I'm gonna put a dot, dot, dot to say that continues on to include our purple, okay? But each of these is gonna have our 1/9 probability. I will know whether or not you listened to the video by whether you yourself wrote out the rest of them or not. So please make sure you write out the rest of the probabilities. You should have 9 total things in your sample space. Okay. Our trick that we use is that we multiply across branches. That's what we were just talking about. So when we are starting at the start and we're moving across the branches, we multiply those values. That's why I multiplied my 1/3 times my 1/3, okay? If I want to combine different outcomes, like maybe I want the probability of green, then I would take anything that has a green probability and I would add them up. So I'd have 1/9 plus 1/9 plus 1/9. When we add fractions, we keep the denominator the same. We combine the numerator, so I would have 3/9. So whenever I'm going down a sample space, I add, okay? We add down a sample space. So when we are combining probabilities, we are adding them. When we are finding the probability across a tree, we multiply. So here's another example for you. I have a 6-sided dice. I roll it, and then I flip a 2-sided coin. So my first action I take is the dice. And there are 6 options. I could roll a 1, a 2, a 3, a 4, a 5, or a 6. 1, 2, 3, 4, 5, 6. I will warn you right now, sometimes drawing trees can be really, really messy. It's okay if you need to erase and redraw so that it fits on your paper. It's also okay if you need to grab a separate sheet of paper to draw your tree on. So that represents our dice. Next, we flip a 2-sided coin. Oh, before I write that, the probability of each number is 1 out of 6. There's a 1 out of 6 chance of rolling each number on a dice. Okay, next I'm going to flip a 2-sided coin. There are 2 sides to that coin, so there are 2 possible outcomes. I'm going to move my word dice here. There are 2 possible outcomes for the coin. I can roll heads or I can roll tails. Each of them has a 1 out of 2 chance of happening. Heads and tails, 1 out of 2, 1 out of 2. And it's going to be the same thing regardless of what happened with the dice. Okay. So then in my sample space, I'm going to include all my possible outcomes. So I start at the top. Oops, I could roll a 1 and flip heads. So the probability of 1 and then heads, which would be my 1 out of 6 times my 1 out of 2, or 1/12. You'll notice even before writing them all out that all of my probabilities in the first set of branches are the same, and all of my set of probabilities in the second set of branches are the same. So my total probability is going to be the same for all of them. So if I don't roll heads, I roll tails, and I get a 1/12 chance. Next, I go to my next branch. Probability of 2 in heads is a 12th. Probability of 2 in tails is also 1/12, and we keep going on. You should continue to write all your outcomes so that you have a total of 12 pieces in your sample space. Okay? All right. Now, some situations are slightly different. We have the same situation, but in this case, I'm going to use experimental probability. Before I was using theoretical probability. I said a dice has 6 sides, so there's a 1 in 6 chance. A coin has 2 sides, so there's a 1 in 2 chance. Experimental probability is using that data that we actually collect. So I rolled a dice, and I rolled a 2, a 3, a 5, a 4, a 2, and a 3. Okay. Oh, and I did it one more time. I got a 6. I also flipped a coin 3 times, and I got heads, tails, heads. So if I write out some new probabilities using this, okay, my probability of rolling a 1 is 0 out of 7, because I had 7 total possible outcomes, and I got a 1 0 times. My probability of a 2 is 2 out of 7. Probability of a 3 is 2 out of 7. Probability of a 4 is 1 out of 7. Probability of a 5 is 1 out of 7. And my probability of a 6 is 1 out of 7. You'll notice my denominator is different. It's not 6, even though there are 6 sides to a dice, because I'm using the data I collected, and I ran that experiment 7 times. The same thing goes for heads and tails. My probability of heads is 2 out of 3. My probability of tails is 1 out of 3, because I have 3 total times that I ran the experiment. So now when I draw my tree, I still am going to start with the dice. But this time when I draw my 6 branches, 1, 2, 3, 4, 5, 6. I always mess up the start there. And I have my possible outcomes. The probabilities I write are going to be 0 out of 7, which I'm still going to include. Even though it didn't happen, I still am going to include it in my tree. 2 out of 7, 2 out of 7, 1 out of 7, 1 out of 7, 1 out of 7. And same thing goes for when I do my heads or tails. I still have 2 options, so I still only draw 2 trees, but the probability is now 2 out of 3 and 1 out of 3. Heads or tails, I don't need to write heads twice, but I write 2 out of 3, 1 out of 3. Ooh, that's a funky 3. Heads and tails, 2 out of 3, 1 out of 3, and so on and so forth. Okay, so that should continue down the way. and you should write all of those out. So pause the video and finish it off. So now as I write my probabilities in my sample space, I still write the probability of 1 and then heads, but in this case, my probability is 0 on a 7 times 2 on a 3. Well, 2 times 0 is 0. 3 times 7 is 21. So I have a 0 on of 21 chance. Does that mean that I did this 21 times? No, but that's what the probability total value was. Next, I have the probability of 1 and tails. So I have 0 over 7 times 1 over 3, which is 0 out of 21. Even though the probability of heads or tails are not the same, our total probability becomes the same. Next, I have the probability of 2 and heads. Well, 2 is 2 on a 7. Heads is 2 on a 3. So I have 4 out of 21. And then when I have tails, probability of 2 and tails, I have 2 and 7 times 1 and 3, which is equal to 2 out of 21. You should continue this down all of your probabilities and check and make sure that you have a total of 12 things in your sample space. So that is an introduction to trees. We will do some modifications of it and changes to it that will give us some different results. But for now, this is the basis. Okay, please make sure you've written out your entire sample space.